The Large Hadron Collider. What is it? What does it do? And will it destroy the universe when we switch it on? Imagine, if you will, an intelligent species of alien lost on a planet way out in the void of interstellar space. Their name and physical appearance are irrelevant for now, but their achievements are not. They are quick learners, with minds full of questions. Their curiosity drives them toward every horizon, like insects towards the light. These strange creatures find mysteries literally irresistible. In a few 100,000 years their genetic line has gone from crude stone tool making all the way up to harnessing the power of their home star and seeing to the far edge of the universe and, to at least some extent, understanding how universes work. One day their species is cracking rocks open, seeking a sharper edge, a deeper cut. And then, seemingly the next day, using everything they have discovered and learned about reality, they decide to build a huge machine consisting of millions of components, designed to probe deeper and dissect the very substance of their universe, just to know a little more, still seeking that sharper edge, that deeper cut. They have acquired the technology to see and move individual atoms. They have learned how to harness the energy by which stars burn, and have even made small stars in their laboratories. They have sent robotic spacecraft to the furthest edges of their solar system, and already have plans to begin the colonization of that solar system, always with their eyes on planets around other stars. When they look to the future, they instinctively look into space, to other suns. They don't talk about it much. Hardly anyone says it out loud, but everybody knows deep down what they're really looking for are other planets like their own. They're looking for a new home, another Earth. Of course, I'm talking about us, humanity. And that little science fiction story wasn't science fiction. It was only science. There was no fiction. To everything else in the universe, we do live in deepest outer space, and we would be alien. We have solar power, and furthermore we'll have nuclear fusion, the power of the stars, sometime this century. We have already duplicated the fusion process and have therefore created miniature stars, albeit ones which only shine for a fraction of a second, and we have built a massive machine, a device to probe the secrets of reality. This machine is called the Large Hadron Collider. It is called the Large Hadron Collider because, well, it is kind of big, consisting of a ring 27 kilometers in circumference and a main detector 7 stories high. And it makes hadrons collide, a hadron being the name given to any subatomic particle that feels the strong nuclear force. It is a machine of almost unimaginable subatomic violence. It is the sharpest blade of all, a keyhole on reality, a time machine. But it's also a bit like that first ever tool, a large rock, wielded with the express intention of smashing something to bits. A few words about atoms. To give you a quick idea of scale, an atom is as large compared to an apple as an apple is to the planet Earth. If we want to visualize the size of an atomic nucleus, a good idea is to imagine an atom now the size of St. Paul's Cathedral in London. And on this scale, the nucleus, the ball of protons and neutrons, would be the size of a pinhead floating at the center of the dome, for the nucleus is 100,000 times smaller than the atom itself. Seeing as protons and neutrons have 2,000 times more mass than an electron, the other constituent part of an atom, it's interesting to note that pretty much all the weight you feel when you pick up an object is down to the nucleus, those protons and neutrons. It is impossible to actually see an atom, much less a proton. You can measure an atom's approximate position with a tunneling electron microscope, but you can't actually see it because it's smaller than a wavelength of visible light. Indeed, to an atom there is no such thing as light, only vast waves of electromagnetic radiation and the unimaginably ordered motions within each atom itself, the whizzing electrons, and the protons and neutrons at the nucleus lock tightly together in the embrace of the strong nuclear force. This force works between quarks, binding 3 of them together to make a proton or a neutron. This force also has an influence on the protons and neutrons next door, holding the atomic nucleus together while the electromagnetic repulsion between the positively charged protons is trying to blow the nucleus apart. But the strong nuclear force is stronger, 100 times stronger than the electromagnetic force. This, incidentally, explains the unstable nature of any atomic nuclei that get close to having 100 mutually repulsive positive protons, and why there are only 92 naturally occurring elements. And before you go thinking electromagnetism is a bit of a wimp, bear in mind that the force of gravity is about 1,000 trillion times weaker than the strong nuclear force. We don't feel the strong force because it only operates over distances comparable to the diameter of an atomic nucleus. If gravity were as strong as the strong nuclear force, you would weigh as much as a galaxy. So the strong force isn't called strong for nothing, and this is what holds a proton together. So you can see that it is hard to break a proton apart. The only way to overcome the force that holds it together is to use greater force, and that is what the Large Hadron Collider is going to do. By building the LHC, humanity is, in a way, going back to the stone tool-making days, when we used to smash things to pieces and looked inside for something useful, or maybe something just interesting. The LHC effectively picks up protons and sends them in opposite directions around a magnetic field 27 kilometers in circumference at almost the speed of light. That's 50,000 times around the ring in a second. Then the magnetic fields are lined up, making the protons smash into each other head-on, producing a shower of quarks and other fundamental subatomic particles. The resulting concentration of energy is, in effect, the recreation of the universe as it was around 1/1,000,000th of a second after the Big Bang, the Hadron Era, as it is known, when the temperature was so high that the only matter that could exist were quarks. Some people have shown concern over the suggestion that the LHC might tear the fabric of space-time and thus destroy the universe in a flash, or create a black hole that eats the whole world. In either case, you won't feel a thing. Certainly not if we set off another Big Bang, as some others have suggested. But you don't have to worry. The Big Bang was something else entirely. The LHC cannot generate the energies found at the Big Bang. All it can do, and all it will do, is reproduce the conditions and take a snapshot of how matter behaved just after the B of the Bang. The LHC will watch particles writhing into existence out of energy, just as it happened just after the very beginning, somewhere around 13 to 14,000 million years ago. The LHC is a noble machine, built by a mostly noble race living in the depths of outer space, with the noble intention of finding out just a little bit more about where they came from. So when someone asks you what does the Large Hadron Collider actually do, you can tell them it takes pictures of what universes do just after they are born. And if that doesn't impress them very much, well, in the words of Shakespeare, fuck 'em. The Large Hadron Collider goes live on the 26th of November 2007. But don't worry, you won't feel a thing. And remember, kind viewer, religion sucks for exactly the same reason science rocks, because science is real.